In this lesson, we're going to introduce you to one of the most important parts of your engineering drawing, tolerances. In fact, these tolerances are why your drawing exists in the first place, to make sure we communicate exactly what is required for this part to be manufactured or inspected. So let's first discuss how we may think of parts in our head. And usually we think of them as perfect. Perfect shapes, sizes, things like that. In fact, our CAD models are designed in the part's perfect state, exactly in the ideal way we want them to be. However, there's a truth about perfect parts. They don't exist. Consider how parts are made. No part will ever be made absolutely perfect. If you have any interaction with your production or inspection process, you know this to be true. A part may look perfect at a macro level, but a micro view could show many imperfections. So in the case right here on this machined surface, the surface may look flat. However, if we took something called a profilometer, which is a device that measures surface roughness, and measured the surface, we would clearly see that it is not. In fact, if you ran your fingernail across the surface, you'd probably notice bumps and ridges. It's not a perfect plane. Perfect parts are also unattainable due to things like improper tool usage, or worn tools, machining errors, programming errors, material stresses, inspection methods, employee skill levels, environmental conditions, or many other things, including just sometimes bad luck. So how do we define what level of imperfections are acceptable? For example, holding your phone in your hand, you can see that it has probably a width, a height, and a thickness. But how wide is too wide for them to have a repeatable process on their phone? Or too tall, or too thick? What is the tolerance on those dimensions that would be acceptable, that if they produce that part at the end of the day, they can accept it? Well, we dictate how much we can accept with tolerances. A tolerance is the acceptable range of dimensional variation that still allows for proper function of your part or assembly. The variation defines the maximum and minimum limits for the dimension, geometry, or any other limits that we have to set on the part. For example, we know the diameter of this shaft isn't perfect, even though it shows it to be in the CAD model. What we would have to do is apply a tolerance to control the diameter to make sure that it properly functions when it gets into its assembly or when it gets to its final operating conditions. We do that by putting dimensions on our parts like this. Now, this still does not have a tolerance to it. To start, we are just saying that the perfect or the ideal would be this 3.585. But we still need to know what is acceptable here. Here are some examples of ways that we're adding tolerances now to our ideal part. We're showing what is functionally acceptable, or what the manufacturing limits are for this diameter. These are several tolerancing methods that we will be discussing later, but it's important to know that we're putting limits here on this part. Now we know what is acceptable here.